Here we go, 3, 4, zeros of polynomials. We're going to use something called the fundamental theorem of algebra, which I've already talked about it. And so it's not a big deal. We're going to find all rational zeros of polynomials. We're going to talk about conjugate pairs, and that's how solutions happen when they're complex roots or complex zeros. Factoring again. We're going to use this French guy's name. His name's Descartes' rule of signs, and that's going to tell us what the possible solutions can be if they're there. Upper and lower bounds to find zeros, and zeros of polynomials in real life applications. So here we go. If we're talking, so here's the fundamental theorem of algebra right here. In the complex number system, an nth degree polynomial has exactly n zeros. There it is. That's the fundamental theorem of algebra. So whatever n is, that's how many solutions there are. Is that how many real solutions are there? No. I'm talking about the complex numbers. Okay. In the complex set, that's how many answers there are. Okay. The fundamental theorem of algebra came from this guy, this German mathematician named Gauss. If f of x is a polynomial of degree n, where n is greater than 0, f has at least 1 0 in the complex system. That's all there is to that. Okay. Using the fundamental theorem of algebra and the equivalence of zeros, you can obtain the linear factorization theorem. I can take any polynomial f of x, and I can rewrite it in this form. A sub n, that's just going to be, we've talked about a, right? Your leading coefficient. Okay, we talked about a. So this is going to be your leading coefficient. There might be some changes based on the x's, but we have x minus c sub 1, x minus c sub 2. Each of those c's represents a complex solution. Okay, a very basic example. That it's not going to have well, real numbers are complex, aren't they? Okay, so if I had f of x equals x squared minus x minus 6, that factors easily, doesn't it? Two numbers to multiply to get -6, but we'll combine and get -1. What does that factor into? Okay, x minus 3 times x plus 2, right? That's what this is showing. What is my a sub n in the example I just gave you? What is this number in the very front here? A 1. Okay, so my two complex solutions, though they're real, are, what are the two solutions? What solution comes out of x minus 3? The solution is 3. What solution comes out of x plus 2? -2. Okay, so that's what this is showing. Okay, this particular polynomial had a second degree, which means this second degree polynomial has exactly 2 factors. Okay, let me give you one that's complex. F of x equals x squared plus 1. That doesn't factor, does it? Okay, because this actually would factor into x equals plus or minus the square root of -1 is what it would factor into. What is the square root of -1? So this actually factors into x plus I times x minus I. There you go, 2 complex solutions. But again, I started with a second degree polynomial. I end up with 2 factors. Okay, questions so far? Yes. Yes. That's the number. That is the number. Yes. The fundamental theorem of algebra and the linear factorization theorem tell you only that zeros or factors of polynomials exist. It doesn't tell you how to find them. If I have a 5th degree polynomial, it has how many zeros? 5. Do you know what they are? No. All this tells me is how many there are. Okay? It tells me that they exist. The first degree polynomial, f of x equals x minus 2. What's the degree of that polynomial? 1. So how many zeros does it have? 1. Where is it? At 2, right? Because you set this equal to 0, x minus 2 equals 0. That means x equals 2. Multiplicity. We haven't really talked about multiplicity. I've kind of thrown it in there from time to time. But multiplicity happens when the exact same 0 repeats itself. Okay? F of x equals x squared minus 6x plus 9. How many zeros does it have? 2. This guy factors into x minus 3 times x minus 3, or we could write that as x minus 3 squared, telling me that this factor happens twice. That's what exponents means, right? Exponents tell you how many times to repeat a factor. So this quadratic has 2 solutions. One of them is 3, and the other one is 3. So instead of saying the solutions are 3 and 3, we would say the solutions are 3 with a multiplicity of 2. That making sense? Okay, that's a repeated 0. I think this text likes to call it repeated zeros. Every text I've used in the past has called it a multiplicity. Isn't repeated mean multiplicity? Multiplicity means it's happening over and over and over again. Okay. Third degree polynomial. How many zeros? 3. This particular polynomial, I can factor, and the first step of factoring is always the greatest common factor. If I factor out an x, I'm left with x squared plus 4. And then they just kind of jump ahead. Y'all might ask yourselves where that come from, right? Do y'all know where the plus and minus 2i came from? Not right offhand, right? Okay, let's take this x squared plus 4. To find the zeros, you take each factor and set them to 0. If I set this to 0, to get x by itself, step number 1, subtract 4 from both sides. So x squared equals -4. Next step, take the square root of both sides. What is the square root of x squared? X. What is the square root of -4? Plus or minus. The square root of the -1 is I. The square root of 4 is 2, so 2i. So here, that right there, there's the plus 2i right there, right? X minus 2i equals 0 means x equals positive 2i. And there's your negative 2i. So third degree, there's 1 0, there's another 0, there's another 0. There are 1, 2, 3 zeros. Okay. 1 real, 2 imaginary, right? As I was looking through the notes earlier, something that I don't think it actually ever explicitly said, it does in a way. If there are complex solutions, the number of complex solutions will be even, always. You will never, 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 never have an odd number of complex solutions. And complex meaning including the imaginary, okay? Because they happen. Do y'all know do y'all remember what we call this? 2i and -2i? They are both imaginary numbers. What else? What did we call them? Let me write this. We had, I'll write something else down for you. There you go. A plus bi and a minus bi, right? Those are complex conjugates. We'll also refer to these as conjugate pairs. Anytime we have complex answers, they're going to come as conjugate pairs. That's why the number of complex answers is always even, right? Questions so far? Okay. Rational zeros test. Okay. When you are finding zeros, if I have a 5th degree polynomial, folks, we have no tools for solving 5th degree polynomials. If you can get that down to a quadratic, I can do the quadratic equation, completing the square, I can factor. I've got all kinds of tools for quadratics. I don't have any tools for fifth degree polynomials, but I know a fifth degree polynomial has 5 zeros. Now, it's possible, at least one of those is real, right? If it's fifth degree, one of them has to be real. What about the other 4? They could be real or they could be imaginary, okay? So to find these zeros, what we're going to end up doing is let's choose a number and use synthetic division and divide and see if we get 0 as a remainder. How many numbers can you choose from? We could choose positive numbers. We could choose negative numbers. We could use fractions. We could use positive fractions, negative fractions. So what the rational zeros test tells us is, hey, you know what? I know there's a lot of numbers you can choose from, but these are the only ones that might work. I'm not saying they will work, but these are the only ones that might work, okay? That way you're not just randomly choosing numbers that I guarantee won't work. Because if you choose a number that's not one of these rational zeros, I guarantee you it won't work. So the way this is done is P divided by Q. P is the constant. Q is the leading coefficient. Okay. I've seen people get these mixed up. I'm going to say something. It might be a little on the crude side, but it is what it is. P comes out the end. That's where you're going to find the P. Okay. Y'all with me? So P is going to be the coefficient. If you look closely at the way they write the Q, that kind of looks like an A, which is going to be your leading coefficient. Okay. So make sure P goes on top, Q is on the bottom. Okay, P is on top, Q is on the bottom. It's alphabetical, isn't it? Reading top down, like we read a book, top down, P, then Q. Okay. Questions on that? I just throw some stuff out there to help you remember which is which. So to find the rational zeros, the numerator is going to be all possible factors of P, and the denominator is going to be all possible factors of Q. Now, when your leading coefficient is 1, life is easy because you're taking all the possible factors of P, which is your constant, divided by 1. Well, that's just going to be the factors of P, correct? If A is 2, now we're going to have denominators of both 1 and 2 because the factors of 2 include 1 and 2. A little confusing right now? Okay. Lots of words, lots of letters. Let's move on. I want to find what are the possible rational zeros of this 4th degree polynomial. Okay. What is my P for this problem? Okay, -6. And honestly, we can ignore the sign. Okay, because it's not going to matter. Q. What is Q for this problem? 1. So what I want to know now is what are the factors of 6? What all numbers go into 6? 1 times 6. What else? 2 times 3. Anything else? Okay. There's 4 more. Every one of these are plus or minus, plus or minus, plus or minus, and plus or minus. Okay. 1 goes into 6, so does -1. 2 goes into 6, so does -2. That makes sense? Okay. What are my factors of Q? Plus or minus 1. Which means the only possible rational zeros of this 4th degree polynomial are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. If I was trying to use synthetic division, would choosing the number 5 be a good idea? No, it's not possible. Okay. Would choosing the number 1 make sense? 1 could work. It's one of our choices, right? So if I was using synthetic division, now if I wanted to see if 1 works, so I'm going to try 1. My coefficients are 4th degree, 3rd degree, 2nd degree, 1st degree, and my constant, right? What do I do? First number comes straight down. Now what do I do? Multiply and combine. 1 times 1, 1. Combine those, 0. 1 times 0. Combine. 1 times 1. Combine. 1 times -2. Combine. Not 0. Yeah. Which means x minus 1 is not a factor of this guy. Okay. Real quick, a shortcut to see if 1 works or not. Add up the coefficients. What is 1 minus 1 plus 1 minus 3 minus 6, which is what y'all said a while ago, right? Yeah. So because 1 did not work, let's try something else. I've got 7 more possibilities, right? Let's try 2. My coefficients are the same. 1, -1, 1, -3, -6. Bring the 1 down. Multiply. 2 times 1 is 2. Combine. Thank you. 1, -1, 1, -3, -6. Okay. Combine and get 1. 2 times 1. Combine. 2 times 3. Combine. 2 times 3. Remainder. Which means x plus 2 is a factor, right? And if I take the x plus 2 out, see if y'all remember from yesterday, what's left? What does this represent? This would be 1x cubed, right? It went down by 1. X cubed plus x squared plus 3x plus 3. And we could keep going. Now, let me ask you this. Can 2 work again? It could. It's possible. Let me ask you this. Can 1 work? If it didn't work before, it's not going to work now. And what I'm saying is, once we have this depressed polynomial, the next time I use synthetic division, let's use this one and not go back up to this one, because now it's going to be a little bit shorter trying to find the next 0. Okay. All right, moving on. They can open the door if they want to come in. So they tried -1. -1 did work. Here's what I'm talking about now. They tried -1 first. They got -1 to work. They then tried 2, but notice they used the new polynomial here instead of going up to the original. Okay. Obviously, if it's going to work in the new one, it's going to work in the old one. Okay. And so they found out that 2 works. Once they found out that 2 works, they now have, down at the bottom here, x plus 1 times x minus 2 times x squared plus 3. So there's your x squared. We have no x's, and my constant is 3. The remainder was 0 both times. This is still a 4th degree polynomial. Okay. Now, what would you do with x squared plus 3? Does it factor? No, it doesn't factor. Can we use the square root method? X squared equals -3, right? Set it equal to 0. So x equals what? Plus or minus I squared to 3. So there are my 4 zeros. My zeros are -1, +2. Those are my 2 real zeros. And my 2 imaginary zeros are plus or minus I root 3. You doing all right? Yes. So these are the 4 zeros, the 4 factors of this. There's a graph of it. Can you see that that graph only touches the x-axis twice? Does it make sense that there's only 2 real roots because it only touches twice? But if there have to be 4, then the other 2 have to be complex or imaginary. And I've already found what they were. Moving on. Where? X squared plus 3 has no real zeros, just that piece. X squared plus 3 produces the, plus or minus square root of 3 i's, When the leading coefficient of a polynomial is not 1, the list of possible rational numbers can increase dramatically. For instance, if the leading coefficient was a 2, we have now doubled all possible combinations because not only are we over plus or minus 1, but we're also dividing by plus or minus 2. If the leading coefficient is 6, we've now added dividing by plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. A lot more possibilities. Okay. So things that we can do to shorten this, and I am not familiar with number 1. I'm not familiar with programming a calculator, but apparently a programmable calculator will help you speed up calculations. Graph it either by hand or with your graphing utility. That's going to help you get. So actually putting these in the calculator and calculating the 0, all of you know how to do that, correct? Okay, you need to get with me. We'll spend some time one-on-one on how to find the 0 on a calculator. But that's going to give you the zeros on the calculator, but it might be irrational or fractional or whatever. So we got to figure that out, but it's going to help you get close. And number 3 is the intermediate value theorem, which we talked about yesterday, where you just choose points to see if it's positive or negative, and then start getting closer and closer and closer. Of these methods, I think number 2 is going to be the most powerful for you to use. Graph it, look at the graph, calculate the zeros, and move on. Synthetic division is how we test the possible rational zeros. So what can happen here is if you find good numbers on the calculator, you can use synthetic division to figure out what your depressed polynomial is. And once you have that depressed polynomial, it'd be easier to find additional zeros, including the imaginary ones. Finding the first 0 is usually the hardest part. If I'm dealing with a 5th degree polynomial, that's a lot of work. Okay. So finding that first 0 might be complicated. Try it over and over and over until we find one that works. Once we get it down to a quadratic, it's a lot simpler. Right. Conjugate pairs, we've mentioned this already. A pair of complex zeros are conjugates. That is, they're the form a plus bi and a minus bi. Let f be a polynomial function that has real coefficients. If a plus bi, where b is not 0, is a 0, then a minus bi is also a 0. Here's what happens. They're going to give you a problem like this one here, and say, hey, one of the solutions is x plus I or x minus I. Find all solutions. If I tell you one of the solutions is x minus I, what must another solution be? X plus I. If I tell you a solution must be 3x minus 2i, what must be another solution? 3x plus 2i. Okay, so if I give you only one complex solution, I'm actually giving you two. Don't forget it. Okay. This question says find a fourth degree polynomial with real coefficients that has -1, -1, and 3i as zeros. How many zeros did they give me? Okay, they explicitly gave me 3. They implicitly gave me the fourth one, correct? Because obviously, if 3i is a 0, what else is a 0? -3i. So now that they've given me the zeros, and this was on your homework for 3-2 without the imaginary stuff, they were giving you the zeros. Where did the -1 come from? It came from x minus -1. But what's x minus -1? X plus 1. So there's an x plus 1. There's an x plus 1. There's your x minus 3i, and there's your x plus 3i. Opposite signs. Yeah, because x plus 1 is a factor, that factor equals 0, which leads to x equals -1. Okay? They tell us to leave a as 1. So folks, this right here is the polynomial. I know on 3-2, it was accepting that as the answer. I don't know if when we move on, if it's going to say, hey, you need to go ahead and multiply this out. So how would you go about multiplying this out? There's no like terms because we're multiplying. What is x plus 1 times x plus 1? Let's go ahead and multiply it out. X squared plus 2x plus 1. Okay. What is, I'm now put that in parentheses. What is x minus 3 times x minus 3i times x plus 3i? X squared plus 9. It's a difference of squares. Okay. And now we could multiply these together. We could distribute the x squared. X squared times x squared is x squared times x squared is x to the 4th. So what I'm doing right there, that's x to the 4th. X squared times 2x plus 2x cubed. X squared times 1 plus x squared. Keep going. The 9 times x squared plus 9x, plus 9x squared. 9 times 2x plus 18x plus, combining like terms. Whoops. What do we got going on here? What's that supposed to be? A squared? That's just a plus. Okay, there we go. Thank you. Final answer. X to the 4th. So that is the 4th degree polynomial with a being 1 that has solutions of -1, -1, 3i, -3i. Ethan, your hand up. Trying to fix your hair. That's a no also. That was recorded. That's beautiful. Okay, so here we go. Here they're working through it. If you want to snap screenshots, that's cool. We did x plus 1 squared. We did x minus 3i, x plus 3i. Moving on. There you go. And I think that's what we got. Yes. Okay. Factoring a polynomial. The linear factorization theorem shows that you can write any nth degree polynomial as the product of n linear factors. That was what we just did, isn't it? They gave us 4 zeros. We took those 4 zeros and wrote 4 factors to represent a polynomial, right? That's what this is saying right here. However, this result includes the possibility that some of the values of Ci are complex, which we just saw in the last problem. And Matthew, this is where you see the x minus C1, x minus is always minus. Whatever zeros they gave you, it's always minus, okay? The following theorem says that even if you do not want to get involved with complex factors, you can still write f of x as the product of linear and or quadratic factors. Which means we could have, when we got to the x squared plus 9, we could have left it right there, okay? X squared plus 9 is written, that is a real factor of the polynomial. X squared plus 9 does not factor on the real numbers. It factors in the complex numbers, okay? A quadratic factor with no real zeros is said to be prime or irreducible over the reals. But I want you to notice there that it says, it does not say it's irreducible over the rationals. So just because a quadratic does not factor easily, we can still solve it with the quadratic formula, can't we? And even if we get a real answer, it might be irrational, but that's still real, right? Irrational numbers are real. Okay. The quadratic x squared plus I is irreducible over the reals. However, we can factor x squared plus 1 over the complex numbers because, well, we're going to change to x squared minus 2. Well, no, we're leaving it there. X squared plus 1 factors into x minus I plus I. Okay, so these are complex factors. But if we wanted to leave it in terms of real, we could leave it as x squared plus 1. X squared minus 2 factors. X squared minus 2 factors into x minus square root of 2, x plus square root of 2. Okay? Find all the zeros of this function given that 1 plus 3i is a 0. If 1 plus 3i is a 0, what else do we know? 1 minus 3i is also 1. Okay? So look how this is written. I have x minus, and they put 1 plus 3i in parentheses, times x minus 1 minus 3i is in parentheses. So they've given us 2 factors. If they've given us 2 factors, what's going to be left? How many factors are left? 2, because it's a 4th degree polynomial. Okay? They want to keep each factor together. They could have done parentheses and parentheses, but a lot of times you do parentheses and then brackets and then braces when you move it out. It's just another grouping symbol. Maybe it's emphasis to show that, hey, this 1 plus 3i goes together, but this whole thing goes together also. Yeah. Okay, so if 1 plus 3i and 1 minus 3i are both factors, then we can multiply those together. If we multiply those together, I want y'all to see how they did this. They changed the groupings, right? Instead of the 1 plus 3i, they changed it to x plus 1 or x minus 1. What property did they just use? The order stayed the same. They changed the grouping. They used the associative property, and that's legal. So now what we have here, if you'll notice, x minus 1 minus 3i, x minus 1 plus 3i. Well, that's a difference of squares. That multiplies into x minus 1 squared minus 9i squared. But what's I squared? I squared is -1. So what does minus 9i squared really mean? Plus 9. Now, if we multiplied x minus 1 squared, we would get x squared minus 2x plus 9, right? I mean, plus 1. X minus 1 squared is x squared minus 2x plus 1. Plus 9 gives us plus 10. So this is what we get when we multiply these two together. Moving on. Here's some long division. You cannot use synthetic division when you're dividing by a quadratic, okay? My original polynomial is x to the 4th minus 3x cubed plus 6x squared plus 2x minus 60. Again, I don't like the way they do this, so I'm going to go ahead and we're going to redo this real quick. Y'all could probably use the extra practice on long divisions, right? Okay, so I'm taking this 4th degree polynomial, dividing it by a quadratic. Looking at the first term, x to the 4th divided by x squared. X squared. I only looked at the leading terms. Now I will multiply the entire polynomial on the outside by x squared. X squared times x squared, x to the 4th. X squared times negative 2x, negative 2x cubed. X squared times 10 plus 10x squared. It's now rhyme time. Draw your line. Change your signs, all of them, and now combine, right? X to the 4th minus x to the 4th, gone. Negative 3x cubed plus 2x cubed. Negative x cubed. 6x squared minus 10x squared. Minus 4x squared. Anything else to combine? Bring it on down. Plus 2x minus 60. I can divide negative x cubed by x squared, can I? So because I can, I must. Trenton, if you need to go to the office because you can't keep your eyes open, I'll be more than happy to send you out. Negative x cubed divided by x squared. Negative x. Negative x times x squared. Negative x cubed. Negative x times negative 2x plus 2x squared. Negative x times 10 minus 10x. Rhyme time. Draw your line. Change your signs. Now combine. Negative x cubed plus x cubed. Gone. Negative 4x squared minus 2x squared. 2x and 10x. Minus 60. Can I divide negative 6x squared by x squared? Yes, so I must. X squared goes, negative 6x squared divided by x squared is. Now to multiply, negative 6 times x squared. Negative 6x squared. Negative 6 times negative 2x plus 12x. Negative 6 times positive 10 minus 60. Rhyme time. Draw your line. Change your signs. Combine. And folks, if you don't get a 0 on this, you messed up because they told us what the two factors were. We multiplied those two factors together to get this. If they told us they're factors, then we better get 0. That makes sense. Okay. Because I got 0, I now have this quadratic. I actually wrote this one down earlier. What does this one factor into? X minus 3 and x plus 2. Okay, I don't know why it just happens to be the same one I did a while ago. I don't know. Okay, moving on. Snap it if y'all want it. So we have x squared minus 2x plus 10 plus 10. That is factorable in the complex, correct? Because they gave us those complex numbers to get this, okay? X squared minus x minus 6 factors into x minus 3, x plus 2. So if I wanted to write this original fourth-degree polynomial in real factored form, this right here is the answer for real factored form, because this is only real numbers. And this part right here does not factor in the real numbers, correct? Okay. But we do now know that the zeros are x equals 1 plus 3i, x equals 1 minus 3i, x equals 3, and x equals negative 2. How are y'all doing? What's the likelihood of finishing these 3 assignments by Sunday? Okay, in this last example, if you were not told that 1 plus 3i is a 0, you could still find it. We could still find the real zeros using synthetic division. We could have found these two, which would have brought us to this quadratic. And then this doesn't factor, so what would we do? How would you find the zeros from this quadratic formula? Right? So they gave us 2 complex at the beginning. Okay. Other tests? Do it. All right, I'm gonna have to stop there.